There's one more nice geometric operation that has an easy representation in R2 and R3, and that's stretching vectors. So let's look at R2. Let's stretch by 2 in the y direction. So if we wanted to, so again, we can just look at the what happens to the standard basis in R2 to come up with a matrix for this operation. So if we stretch by 2 in the y direction, well, that leaves the first standard basis vector alone, so it's still 1, 0. But the second standard basis vector, it gets stretched. Instead of, since we're stretching by 2, it doubles in length, so now it's 0, 2. And then we can get the matrix for this linear transformation just by packing these results together in a matrix as columns. So we get 1, 0, and 0, 2. Okay. You can see what happens is, since we stretched by 2 in the y direction, this is basically the identity matrix, but in the direction that we stretched, the 1 for that position in the identity matrix tells you how much you're stretching. Right? So that's why there's a 2 right there. In fact, that's why the identity matrix, right, you can think of this as stretching in the x direction by 1, which doesn't change anything, and stretching in the y direction by 1, which also doesn't change anything. We can extend this to R3 in a pretty straightforward way. We can stretch, let's say, in the z direction by, I don't know, -2. A negative stretch is a stretch and a flip. Okay? And let's compress in the x direction by, let's say, a third. Okay. So in the z direction, so we need to look at the third position on the diagonal in our identity matrix. To do this flip, we need a minus, and to stretch by 2, we need a 2, so -2. And then in the first diagonal position, which corresponds to the x direction, we need a 1/3 to get this compression. The y direction we aren't changing, so that position stays the same. It's still a 1. And so this is the matrix that achieves that stretching operation.